Thank you so much. Thank you for coming. Thank you for the invitation to speak in this environment here that is jointly organized by various UC campuses. Today I would like to talk about Earth's many voices, a unified theory for pre-earthquake signals, and if you have remembered what was announced, I had added here the word tort, because as so often we are well on the way to understand the physics underlying pre-earthquake signals, but of course we are not yet there. These are my collaborators, and two of them are here. Ipek and Gary Sear are working with me at NASA Ames. These are students, my son also at NASA Ames, and these were students that joined the project during the summer, and this is the engineering staff at the NASA Engineering Laboratory where we do most of our large-scale experiments. Now what I want to do, because my background is actually crystallography, and I became interested early on in defects in crystals, and for a long, long time I never thought that it would ever lead me towards the area of earthquake phenomena. So I wanted to go with you first and take you from a single crystal, from the atomic structure, all the way over to questions that are of interest to the planet. Now you all know that we live on a dynamic, tectonically active planet with huge convection cells that take about 200 million years for going through the cycle. And we are sitting here on the skin, and the horizontal component of these convection cells are moving the plates, and the plates are either colliding or sliding or pulling apart, and this makes up this beautiful planet of ours. So the question is, what are the processes that precede the rupture of rocks on very large scales, on the order of fault lines that maybe as long as 1,000 kilometers or more, like 2 years ago in Sumatra, or 40 years ago in the largest earthquake in recorded history in Chile. Before these monstrous phenomena occur, something must happen during the compression, during this stressing of the rocks. And indeed, people have reported for many years, some for centuries, that earthquakes are preceded by signals. The signals are subtle, often fleeting, quote-unquote unreliable, but again and again they have been reported. These are changes in the atmosphere, cloud, fog formation, perturbation in the ionosphere, thermal anomalies that have been detected about 20 years ago from satellite orbit, low frequency electromagnetic emission, and last but not least, strange animal behavior that has always been associated with these phenomena. And you will see this slide several times, and I will go through various points here. And today, first, I want to talk about the coherent and testable theory, solid state, based on solid state concepts, semiconductor concepts, that help us understand these phenomena. So here we go again, this crystal. This is an MgO crystal that grew from the melt at nearly 3,000 Kelvin. That's the crystallization temperature. And the melt contained a little bit of water. You can also put in heavy water, and then the crystal that grows is contaminated with water. Though its stoichiometry is slightly off, and it has hydroxyl in there. And actually you see in here, inside this crystal, I grew this crystal in 1980 in Bristol from with a friend of mine with whom I worked at that time. And you see here that during the cooling, the gases tried to get out of the crystal. Those that didn't make it had to precipitate internally and form these clouds of little tiny bubbles. Now, what we found already, the first paper came out in 76. We found in 76 that these hydroxyl, when they occur as a pair associated with a cation vacancy, they don't stay. During the cooling, somewhere between the 600 and 400 degree centigrade window, these hydroxyls reversibly convert into peroxy plus hydrogen. It's a redox reaction, very common redox reaction like you would have it in many chemical processes, in which an electron is transferred from the oxygen to the proton. The proton, two protons form molecular hydrogen, and you get a peroxy. Now, how does this look? Here you have an ideal structure. It's a very boring, MgO is a very boring crystal. It's cubic, highest symmetry cubic. It's transparent, not much to do with it. I started to work on this in the 70s, and I discovered, to my big surprise, that some of these oxygens have changed their valence from oxygen double minus to oxygen single minus, and they form a peroxy defect. Two oxygen single minus are bond together as in a very short bond. Now, upon heating, you can actually show that this little tiny innocent-looking defect breaks apart in two steps. And the first step is marked by a breakdown of this bond. And if this bond breaks down, the electron density associated with the O- state, this whole state, the defect electron state, spreads out over hundreds of oxygen, and you form first a bipolar ion. And this process, the transition from here to here, can be clearly seen in essentially all physical properties, basic fundamental physical properties of this material, in the thermal expansion, in the dielectric constant, the refractive index, and when the bipolar ion breaks up, you get a paramagnetic transition. Because as long as they are coupled, they are diamagnetic, and when they decouple, then the nuclear spins flip, you become paramagnetic. Then, at higher temperatures, this breaks apart, an electron hops in from the outside, and the electron that is hopped in from the outside then becomes a whole charge carrier that is dissociated from this defect, and this is a well-known defect in catalysis, and that's where my work actually in the 70s and 80s was focusing on. Suddenly you get a surge in electrical conductivity, in this particular case of the MgO, that the electrical conductivity goes suddenly up by up to 6 orders of magnitude. So we are going to focus on these little fellows here. They are defect electrons. They are essentially the electronic wave function associated with a missing electron in the sublattice of the oxygen. People call this a positive hole. Oops, why is it not coming down? Oh, it did. It went too far, sorry. So we can draw this in a very simplified energy diagram, where down here you would have essentially, if you do it more accurately, you would have the K space, and up here the energy. And an insulator is a material, a dielectric, where your valence band and your conduction band are separated by a very large energy value, and therefore this is an insulator because you have essentially no chance of activating electrons from the valence band to the conduction band. But if some of the oxygens in this material as pairs exist there and have changed their valence, they represent a point defect which would make a little depression at the upper edge of the valence band as a positive hole pair, and in the moment they would dissociate and form these hole pairs, these defect electrons, then their wave function delocalizes and you actually get conductivity at the upper edge of the conductivity of the valence band. And the electrons that are formed at the same time, they settle down at a deeper level and they become they are still somewhat localized. These are delocalized electronic states. And it is along this now that the conductivity develops. Now, early on, I became aware that what I discovered with the MGO is universally true. And the only compound so far that I have seen among oxides and silicates, the only oxide material that I have ever been able to show that they don't contain peroxy is sapphire, alpha aluminum oxide. All others seem to have, and carbonate, calcite and marble, they don't have this. But all the others, all other minerals that have ever gone through a high temperature cycle, picked up some water impurity, cooled down, the OH pairs must have changed and formed this defect, point defect. Now this point defect is a dormant electronic charge carrier that just waits to be awakened. And indeed, when we, instead of heating, we choose mechanical stress. If we have mechanical stress, shear stresses, we are generating dislocations. The dislocations are sweeping through the crystal structure in huge numbers. A cubic centimeter of material that becomes moderately deformed produces enough dislocations that if you would put them end on end, you would be able to run to the moon and back from one little cubic centimeter. So efficient is this process of dislocation generation during mechanical deformation. And during mechanical deformation, this bond here is wiggled. As soon as it is wiggled, it breaks apart. And then something very unexpected from our perspective at the beginning was that actually here too, an electron is hopping in this broken bond. The electron settles in here, becomes somewhat localized, and you are generating these defect electrons out somewhere outside the broken bond. And this is then turns this oxygen here, which is symbolized by the SiO4 unit, because anyhow the wave function is delocalized. This turns into an O-, or in semiconductor language into H. That means a hole, a defect electron that is mobile. So to summarize this section here, an O- is a defect electron or hole. People in the glass industry, electron spin resonance people, called it a positive hole, even though it's an oxymoron. And I suggested that we abbreviate it and we call it a phole, because maybe we can use some new words. A phole, therefore, is an electronic charge carrier. It lives in the valence band. It propagates with 200 meters per second. And that is consistent with the theoretical image that the propagation of that hole occurs by a phonon-mediated electron hopping. So the phonons are vibrating at room temperature at about 10 to the 12 hertz. Each time the phonons the atoms would approach each other, electron can transfer more easily. The jumping distance is about 3 angstroms. Therefore, 10 to the 12 times 3 angstrom gives you 300 meters per second. We are measuring 200 meter plus minus 50 as the speed with which the charge cloud can propagate. So they travel fast. And now I'm going to show you in the laboratory, they travel through meters of rock. And there's a good reason to believe that in the field out here, they travel through kilometers. So here's a rock. Tiny little piece, weighs about 200 kilograms. It's 4 meters long. It's sitting here in the Central Engineering Laboratory at NASA Ames in a hydraulic press that can deliver 30 tons, so not a very powerful press. Now we squeeze it at this end here, and these two pistons here, they're about this size. They are connected with an electric wire that runs through this picoammeter all the way up here to the front of this rock, where we attach some copper tape, which is electrically conductive and makes an electric contact through some graphite-loaded glue. So we establish an electrical connection between here and here. And look what happened when we start squeezing. This piece of red granite, 4 meters long, here's in green is the load, here's the time. So as soon as we start loading this rock, a current starts to flow. Not much, about a nanoamp. The current saturates way before we reach the plateau here. And then, as we keep the load constant, the current continues to flow and slowly decays. When we take the load down, the current goes down and then continues to decay with a longer time constant. Now, this doesn't sound much like 1 nanoamp. We just this morning had an experiment at NASA Ames where we had a similar piece of rock, a little bit larger, 300 kilograms or so of rock, and it produced about 10 nanoamps of these currents under these conditions. But if you now imagine a cubic kilometer of a rock, and during a medium-sized earthquake, many hundreds of cubic kilometers of rocks are subjected to increased stresses, deviatoric stresses that would qualify as shear, you would get currents on the order of 10,000s, 100,000s of amperes, capable of flowing out of this stressed rock volume. So the holes, the defect electrons, are flowing through the rock. The electrons cannot flow through the rock because the rock, after all, is an electronic insulator. It has no energy states to flow, at least not at room temperature, through this rock. The electrons, however, can flow through the metal contact here into the piston, and with this wire and an ammeter in between, the electrons come around, shake hands with the holes here, and the current is closed. This is a battery. It's the same thing like your car battery that you may have at home, sitting at the spare in your garage for your car. You have a cathode here, and you have an anode here, and you have a cathode here. And if you connect the two things, a current would flow. Now, the current here, in this case, is limited by the internal resistance of the rock. But if the rock is rather conductive, which would be the case for gabbro or basalt, the more mafic rocks, then you can actually draw here currents. As I mentioned a moment ago, this morning we got about 10 nanoamps. If this would be a piece of gabbro, a black rock, from deep within the crust, we can get tens, maybe even 100 nanoamps out of rock of this size. Now, this rock flows, the charge carriers flow through the rock. We can also put a little device with plexiglass up here and fill this with rock dust, dry. We can wet it, make it wet with sand or soil, and ask, will the current also flow? And the answer is yes. The current flows through sand and soil. And it also flows if we then, instead of putting the copper electrode on the sand, we put another piece of rock on here, and then the contact over here, the current continues to flow. This demonstrates that, now think of the Earth, you have areas where you have one rock type and another rock type, or as you go from deep towards the surface of the Earth and you have let's say, a kilometer or so of sedimentary rock, and on top even of sand and soil, these electronic charge carriers will flow through. The Earth is a huge battery where almost every piece of the Earth, of the continental crust, is electronically conductive for the holes, not for the electrons, for the holes. So these fellows, these pholes, travel not only through solid rock, but they travel through sand and soil. And they get trapped at the surface. Because think of a Van der Graaf. A Van der Graaf is a sphere, could be a solid sphere, can also be a hollow sphere. A sphere of metal, you pump in some electrons and they all end up on the surface because they repel each other inside. It's the same here. The holes repel each other inside and they become trapped at the surface, and at the corners they achieve higher concentrations. And this is the positively charged area, and this is the battery voltage that you can measure. I will show you battery voltages afterwards. Now these voltages, surface potentials, can be calculated. This is a paper that we wrote in the mid-80s. And there's a surface potential calculated for a flat surface of a dielectric medium filling half space. And this concentration of charge carriers, this is 10 ppm, this is 100 ppm. So 1 out of 10 to the 5 or 1 out of 10 to the 4 of the oxygen atoms carried such a whole charge carrier. And you get about half a volt, 400 millivolt. And that value is only a function of the dielectric contrast between your solid and the air or vacuum. In this case, calculated for a dielectric constant of 10. However, the electric field, which is voltage divided by distance over which the field decays, is dependent on the charge carriers and shoots up very rapidly. Here you have the 10 ppm charge carrier concentration, 10 to the 17. Here you have 10 to the 18. And you go from 100,000 volts per centimeter to 400,000 volts per centimeter. And if you would have 10 to the 19, you would go through the roof. That, however, means now we can expect to have very high electric fields at the surface of the rock. And if we get very high electric fields on the surface of the rock, and the rock surface is positive, electrons or molecules, air molecules, can lose an electron to the rock surface and become field ionized. The process of field ionization, that's very common and well known in physics. So let's say oxygen or water molecules are the most likely to be field ionized, and you then get airborne positive ions, and these positive ions will drift over from here to here, and actually suddenly your battery starts to discharge, not because you have run a wire, but you are building up a conductivity through the air. And each electron that is deposited here from a oxygen or water molecule that is field ionized, of course then destroys the surface potential, and you are actually then getting a dynamic system that evolves in this way. Now, when we did this experiment, and I will show you the results, that we did actually these things that we did this summer. Those is very recent stuff. And Ipek and Gary were involved in this work. We found that, as expected, the first thing that we see, that a positive surface charge builds up. Easy to measure. We just put a capacitor plate and measure the voltage between that capacitor plate that floats over the surface relative to the piston. We can measure that battery voltage. Then, when the positive charge has built up a certain threshold value, then the ionization of the air sets in. Suddenly, the air becomes conductive, and we see bursts of positive ions flowing from the rock surface through, let's say, half a centimeter of distance between the rock surface and the rock, and the capacitor plate. And then when we continue to pressurize, we get such high electric fields, particularly at the corners, that we start to see corona discharges. And that then we see free electron and negative ions, and suddenly the current of the ions that flow through the air changes. And I'll show you in the next slide some of these results that are really coming out from, that was done, I think, early this year, and then later I will show you results from the summer. So here's the setup. This is the rock, pieces of rock about this size, and we put them in an enclosure in order to have it dark and that acts as a Faraday cage. Over here we just have a metal plate, aluminum plate, about 10 by 20 centimeters in size, sitting above the rock surface. And here we use pistons, and we make the pistons, we add some teeth to them by gluing some hardened steel bearings at the bottom of the piston, so that actually the stress is very, very concentrated and bites into the rock in order to produce really high degrees of mechanical deformation without breaking the rock immediately. And that is what you see here. As Gary shoots up with a manually controlled hydraulic press the load, these teeth start to sink into the rock, and it takes time for the hydraulic press to recover. During this time, but not closely correlated with these moments of massive deformation of small volumes of rock, here at this end, over here, 20-some centimeters away from where we stress, we then collect positive ions in the air. So we bias this with a negative collector with 90 volts, minus 90 volts, and we measure positive ions. Now look at this. We get roughly, from these currents, we get roughly 10 to the 9 ions, positive ions, per square centimeter per second formed under these conditions. So we see, first step, positive ions. Now we continue with, well, we repeat the same experiment, but now we change the bias on this collector in order to see, when do we see negative ions coming out? Well, that's what we see. We see not much at the beginning. This is already the region where we would see positive ions in large numbers. But here we don't see any negative ions yet. But suddenly, somewhere more than halfway through, this is the breakage of the rock. Halfway through, or more than halfway, suddenly we see bursts of negative charges coming out of the rock, not out of the rock, forming at the surface of the rock through ionization of air molecules. And when we have photodiodes sitting there, and the photodiodes see this characteristic little signals only a few millisecond or 1.5 millisecond long. These are corona discharges that form along the edges of the rock. Because now we are getting into the regime that we are not only forming positive ions, now we get corona discharges, and the corona discharges produce these negative ions and free electrons that we pick up with our collector. So the second step is negative ions accompanied or caused by corona discharges. And still, always remember, we stress at one end here, we measure at another end. Now comes the surface potential, this voltage, this battery potential that I mentioned so often. Remember, you have a battery. Normally, your car battery, you bring it back if it doesn't deliver 25 volts or 24 volts. Here, the car battery, our battery, is a little more delicate. Down here again, the green curve is the load curve. So around this time here, the piston really started to lean onto the rock, and at these points, the rock started to yield, the piston were biting into the rock, and over here is when the rock broke apart. Now look what we see. These, mind you, these are electrostatic measurements, so we measure DC voltages, and they are exceedingly delicate. You have to keep away. You even have to keep your breath, even walking nearby. If it's not sitting in a Faraday cage, if it's sitting in the open and somebody walks by on the floor, just the charge that we build up on our bodies would have an effect on these measurements. So we have to be very careful trying to minimize these effects. So what we see here is that as soon, even the acceleration of the piston, of the press, which goes up and brings the rock piece up. The rock, of course, is sitting supported by the piston on one side and just another support on the other side. This acceleration already creates enough charge carriers to see a little bit of electric charge building up. There, at that point, the piston really makes contact, and the hydraulic press is kind of feeling, am I there? Maybe Gary also turned off the valve a little bit. So we get a little bit of voltage, about half a volt. Then as soon as the charge builds up on the rock, we are building up the battery voltage. But then, as we have reached some level of load, this starts to fluctuate, and the reason for this is that at this point we get this positive charge emission. We deposit electrons from the gas molecules that are being ionized onto the surface, and the surface, our battery becomes unstable because we deliver through air ionization, we deliver electrons to the surface, and then suddenly, somewhere halfway into the deformation, suddenly the surface potential breaks down and even turns negative, again with fluctuations. And that is the point where we get these corona discharge, massive formation of free electrons and negative charges, and the order of 10 to the 10, an order of magnitude more than the positive charges. So this now, when we first saw these potential measurements, we scratched our head and we said, how can we ever understand this? It looks so complicated. And of course, every experiment is slightly different. But this is call it a typical experiment. So now we, I think, have a pretty good understanding of these processes. That first we build up a positive surface charge, then we start to ionize the air, and we get something like 10 to the 9 ions per square centimeter per second. And then third, higher load, we produce corona discharges, and we form free electron and negative ions, and we get ion currents from the collector plate equivalent to something like 10 to the 10 charges produced per square centimeter per second. Huge currents compared to what you would normally expect from such a boring piece like a piece of rock. So, yeah, I was supposed now to go over here on this side. We have essentially, I think, can check off this idea that we are on the way towards understanding processes that happened before during the stressing, long before the earthquake happened. Now I want to go to applications. I want to show you that it should be possible in 10 years and a little bit of funding to produce, to generate, to set up a early warning system, earthquake monitoring system that would be tuned to detect signals that are derived from these things that I just showed you. Surface potential, ionization in the air, formation of electric currents, and another process that I have not yet shown you, which I will show in a moment. So now I want to go through these different, as far as I can get within the time, and I first want to show you what would be the consequence of massive injection of ions into the atmosphere, in the low, at the ground level. I hope you can see this. This is a mysterious website in Japan, a group in Japan that is run by a consortium of private people. They're very uncommunicative. They kind of keep it secret what they are doing. They have set up in Japan something like 10 or so measuring stations in which they measure in a rather elaborate way positive and negative ions in the air, and they distinguish them between small ions, which have a high mobility, and large ions, which are already on the way forming droplets, cluster ions. And what you see up here is a month record of ionization measurements from one of these stations. I think it's north of Tokyo. And there was an earthquake happening about 150 or 200 kilometers north of this that happened just a little bit beyond that time window. And what they see, interestingly, is, it's hard to see for you, I'm sorry, that they often see positive ions. These are the large positive, no, these are the small positive ions, and then the blue ones would be the large positive ions. And you see here bursts of positive ions, bursts of positive ions. Occasionally they also see negative ions. Sometimes, as here, you only get positive ions, no negative ions. You never, in all the records that I have seen, they never observed negative ions without having also observed positive ions before that. That's consistent with what we seem to see, that the first step of a buildup of stress in the deep underground would be accompanied by the emission or the formation of positive ions, and then if it gets worse and worse, you get negative ions in addition. Here's another record. Here they only reported positive ions, and you see how massive these processes can become. So there is a possibility of using such information, but as I said, unfortunately, I have not been able to establish contact with the people who run this station, so I sent him several emails, and they never replied. I want to show you something that some of you might remember a year ago, October 30, at 8:29 or so in the evening last year. There was a magnitude 5.4 rock here, a little bit east of Milpitas. We felt it very strongly. I was at home in Los Altos, which is just around, well, probably around here, or here at Ames Research Center. We got a good shake out of this. Now, it so happened that a small company by Tom Blyer in Palo Alto has established already 70 metering stations along the San Andreas faults, measuring with 3-axial magnetometers the ultra-low frequency emission from the ground. And this station here had fortuitously also incorporated, just a few months earlier, air ionization measurements. So I show you now first the air ionization measurements that were recorded, and the station was, by good luck, just 2 kilometers away from the epicenter. So they were really close by. There was another station here in Portola Valley, about 40 kilometers at a distance. And there are another station up here, but this did not have a air ionization measurement. So what did they see? And I will come back and show you afterwards the low frequency electromagnetic. For the moment, I only showed you the air conductivity. Here, this is the quake day. In the evening at 8:30, 8:29, the earthquake happened. That was 2 days before, 1 day before, and that's the quake day, and this is the quake +1 and quake +2. So you see, this is a typical background. There was not much ionization, except for what you normally have from radioactive decay, radon, and cosmic ray ionization of the air. Then, on the day before, there were blips of increased ionization, and then suddenly, during the night, and it was dry, it was not raining at that time, actually the sensor saturated. And I have to take the blame because I told them how to design the sensor and they did it, but it didn't have enough of a dynamic range to cover the enormous increase in air ionization that was encountered. Then the air ionization, the air became less ionized a few hours before. This is 24 hours here, and then the earthquake hit. And during the aftershocks, there are little spikes. So indeed, there are field observations that Tom Blyer has done in this system, and you will find it. You find these data if you Google the QuakeFinder website. They have this information on their website. And as I showed you before, the data from Japan. So we can check off this one here. So now let's look at the perturbation of the ionosphere. The ionosphere starts at about 90 kilometers and of course extends upward at no end, and typically the effects, ionospheric effects, are considered to happen in this 50 to 1,000 kilometer height range. Now for decades, pre-earthquake ionospheric perturbations have been noticed. The first people who noticed it were in the 30s or so, or even in the 20s. At the time, they started to use radio communication, sending radio waves around the globe, and they are always reflected at the ionosphere and back at the ground and reflected again. That's how they long wavelength radio waves travel around the ground. And sometimes they saw strange behavior. Of course, the ionosphere is very dynamic day and night because it depends on the solar irradiation, the ionization that is produced by the UV radiation. So the ionosphere is a very dynamic system. But when the earthquake happened, then this ionosphere is perturbed. And people have known this for decades. But nobody really understood, until now, really understood what is happening. Nowadays, with GPS technology and all this, it's relatively easy, straightforward. Again, funding is a big issue. That by occultation, so you have a GPS satellite coming over the horizon, you look with this satellite to this satellite, and you see as the beam scans through the ionosphere, you can deduce from the refraction and the phase shift of the beam, you can deduce information about the electron density in the ionosphere and other properties that are typical for this plasma range. And if you take several stations here, particularly stations that are in a row, then you can really do radio tomography. And what you then get is something like this. On the left side, this was a magnitude 6.4 earthquake in Alaska. Doug Regenthaler and his group, which includes some very high-power Russian scientists who do this tomography. The earthquake happened at this spot, and this is a two-dimensional projection of the anomaly of the ionospheric perturbation. So the natural variation is taken out, and only the anomaly is presented here. Although this is a 2D presentation, and these now are the tomography of the ionosphere. And what you see here, 23 hours, 20 hours before the earthquake, how the ionosphere starts to be structured, and how the structuring seems to be focusing to this point here. This is where the epicenter would then occur 23 hours later. Then 30 minutes later, this starts to blur out, and 2.5 hours, the phenomenon disappears. So this is tremendous possibility now to use ionospheric perturbation by designing the software and the techniques to do real-time or near real-time tomography of the ionosphere over earthquake-prone regions. And that's what is happening. Here on the right you see a plot from the 1985 paper. This is published in the book by the National Academy of Science, The Electrical Environment, or the Earth's Electrical Environment. What happens above big thunderstorms? This is 100 kilometers. So at about 10 kilometers, you might have a huge thunderstorm. The thunderstorm produces electric currents that connect to the ionosphere, and these are electric currents calculated for two situations: vertical and horizontal magnetic field lines, so equatorial or polar regions. And you have these connections. And nowadays, at that time, people didn't know anything about the sprites and the elves and all these discharges that happen between the top of the and here. But now this has become much more complex. If instead of a thunderstorm, we have the situation like this here. This is calculated by Valery Sorokin in Moscow. You would have a vertical electric field associated with the injection of ions at the ground level. This is very similar to what you would have in a thunderstorm environment, except that now your field lines start really way down in the surface, on the surface of the Earth, and this would work in fair weather conditions with blue sky and would have an influence on the ionosphere, because such electric current lines that would connect change the electric field. The electric field between the ionosphere and the Earth is about 180 kilovolt, plus minus 100 or so, day and night, between the bottom of the ionosphere and the surface of the Earth. And if this electric field profile is changed by the injection of ions at the ground level, of course the ionosphere will respond. And suddenly now, through this ionization work, we seem to be well on our way to understand how these phenomena are changing. This is, let's say here, look at this. Here's plotted on a logarithmic scale you cannot read it, the ionization rate in ion pair per cubic centimeter per second in the air. So this is how many ions and free electrons are produced by radioactivity, radon, other radioactive elements, here by cosmic rays, which essentially in the low atmosphere decay to a constant value. And I don't even cannot read this myself. Oh, this is backscattered. So the cosmic ray that hit the surface of the ground generates secondary radiation, which is ionizing and produce this level. So somewhere between 1 and a few hundred ion pairs are being produced per cubic centimeter per second at ground level. Now remember, in the laboratory, we don't know yet in nature, but in the laboratory, we are producing 10 to the 9 to 10 to the 10 ions per square centimeter. This is the source per second. So therefore, if we should extend this several orders of magnitude, and if we do so, of course, the electric field distribution between, this is here from ground level to 10-kilometer height, the electric field will change, and it is understandable that the ionospheric response will be instantaneous in response to the changes in the electric field. So we can check this off. We can say, yeah, we are well on our way to understand why there are, and in fact why there should be, perturbations in the ionosphere in response to processes that happen 10, 20 kilometers below the surface of the Earth due to processes at the Earth's surface. Now it comes to something that I haven't even mentioned yet, and that is thermal anomalies. Pre-earthquake thermal anomalies are a very hot topic, very controversial, very contentious. It was first reported by Russian, actually, and then by Chinese researchers in the late 80s and then early 90s, and everybody said, this cannot be true. What people are seeing or reporting is that when they use satellite imagery, using onboard infrared cameras that fly on NASA satellites, on NOAA satellites, even weather satellites, you look at the surface of the Earth from great height, and you watch over many days how the temperature of the surface changes. Of course, it changes day and night and day and night and day and night, and it has a seasonal change. And then these people reported that prior to large earthquakes, days before, rapidly changing areas of enhanced infrared radiation were observed, sometimes as large as 500 kilometers, sometimes elongated along fault lines and so on. Several days before, they spread over large areas. They seem to be characteristically unstable, fluctuating at a tune of probably hours, maybe even tens of minutes, that these areas come and go. Nobody knew what they are. The satellites see an increased temperature radiation, mid-infrared radiation, and therefore they call it thermal anomalies. They thought the temperature of the ground increases, and everybody was, well, not everybody, those interested went down and put a thermometer to the ground and looked at the local meteorological station, and they say, we don't see any temperature increase, or we see a small increase, much too small to explain, sometimes 4, 5, up to 10 degrees increase in equivalent infrared emission in temperature equivalents. So I'll show you first my approach, and these were data that were recorded in, I think, 2002. We did this down at San Jose in the engineering department. I had the idea, I knew from work that I had done in the 80s or 70s even, that it costs energy to break these bonds. Of course, always costs energy to break. But we knew how much energy it costs. We know that it costs about 2.4 electron volt. Therefore, I was reasoning that if something happens like here, this is a cross-section, very simplified cross-section through the Earth. So this is the first 30, 35 kilometers. Stress builds up somewhere, charges are produced, they come to the surface of the Earth. They are trapped at the surface. Why not considering that they would recombine? Of course, a positive hole is positively charged, so they would repel themselves electrostatically. But if by recombination they can gain energy, there is a finite probability for them to recombine. So, if this oxygen here traps a hole and the neighboring oxygen traps a hole, what they do, they will snap together and form again a peroxy bond at the surface. Now, what is special about this peroxy bond? That poor peroxy bond has to pick up 2.4 electron volt or something nearby in vibrational energy. They are born in a very, very excited state. Now, 2.4 electron volt is equivalent to 30,000 degree Kelvin. So these two atoms that are participating in this recombination have a vibrational energy equivalent to 30,000 Kelvin. And the only way for this vibrational energy to really, for these excited atoms to really then thermalize and come back to ground level is to shoot off photons. And these photons should be equivalent to the energy spacing of their vibrational manifold. And we know that. There are high-level quantum mechanical calculations for this bond, infused silica, because this defect is actually of great interest to the optical fiber industry. High purity fused silica. This is the main enemy of long distance optical cables that would transmit optical signals in the near infrared, because that is a defect that is easily activated and then creates color centers which mess up the transmissivity of long-term 100-kilometer long optical fibers. So these have been attracted a lot of attention also from theoretical people, and they calculated the energy of these vibrations. And from this we know that at least at the ground level, the last, as this would tumble down the vibrational excitation scale, the last step here is at 10.7 micron or 930 wave numbers. Another way, of course, is that as they tumble down, they kick their neighbors, and their neighbors would also be excited and emit enhanced secondary infrared photon a little bit at other frequencies. Okay, so let's set up an experiment. And this I did with a Bowman spectrometer that is actually a NASA spectrometer that is used to correlate when the satellite flies overhead. They bring it down in the Nevada desert or so and measure the spectrum of the ground in order to correlate what the satellite sees and what a high resolution, high quality laboratory FTIR infrared spectrometer can see. So here you see the familiar setup, except here we now have the insulator already between the piston and the rock was totally insulated, had no connection, so we don't drain charge carriers from it. And then we started to squeeze. What we did, and we look here at the front of this rock, half a meter away from where we squeeze. And the beam here has about 5 centimeter diameter that were collected with this Fourier transform interferometer. And we first set it up, let it rest, let everything thermalize, the room was dark, the air conditioning worked fine, and everything was stable. For 6 minutes, we recorded the baseline, and then we started to squeeze until the rock broke, which took about 36 minutes, so we didn't go very fast. We slowly increased. On the left, you see the actual spectra. So here you see from 8 micron to 12.5 micron. And what this is up to this line which says start loading. So this is the time axis. This is the intensity. And this is the time axis, and the experiment was ended by the rock breaking. So as you see, in the moment we start squeezing, here the infrared emission spectrum of the surface of the rock half a meter away is changed. Now we don't have millisecond or second time resolution with this Fourier transform experiment, but it's near instantaneous. So we took these, made the average, and subtracted those. This is the excess radiation energy that is emitted from, and what you see here are these narrow bands. And this band here, believe it or not, is at 930 wave numbers. It is exactly where you would expect the last transition from the quantum state, vibration excited state, quantum state 1 to the ground state 0. And then you see the series of other bands at longer wavelengths, and we don't see any further because the light, this was done in optical, in air, so we get cut off by the moisture and CO2 in air. All these experiments have to be repeated in pure nitrogen and so on. So, you see, we see a spectroscopic signature that is characteristic of a process that is consistent with what we have known through the other laboratory experiments from the behavior of the rock, the recombination of positive whole charge carriers, and the first layer of these would emit electrically or vibrationally stimulated. So this is not temperature. It's like an LED. It's a non-thermal emission process, stimulated emission, controlled by the quantum transition between vibrational excited states. So now how do they look in nature? Now here, this is a paper that was published this year from Arun Saraf's group in India. They were looking at many years of satellite images using NOAA AVHRR satellite, and there was a magnitude 6.4 at that day, which is February, the 22nd of February 2005, at this location. 1 day before, 2 days before, 3 days before, 4 days before, they were starting to see an increase in emissivity from the ground in this region here, this region here, this region continue to increase. For some good reason, or some fortuitous reason, the polar orbiting satellite, this AVHRR satellite, every time it passed over it saw this, that either this was a very stable emission process, or we were just lucky that each time this infrared emission happened. And the day after the earthquake, it started already. It's almost completely disappeared. Now, a group in Oxford analyzed the vertical displacement before the earthquake and after the earthquake, as you see, using INSAR, interferometric radar, on some of the satellites. You can measure very accurately with centimeter, even millimeter accuracy, the displacement of the surface by subtracting an image that was taken before the earthquake and an image after the earthquake. Wonderful work that people are doing. I don't know how they do it, but it's beautiful. So this group in Oxford was looking at the displacement of this, because this earthquake actually happened, the epicenter of this is actually to the side. It's not where the infrared emission comes from. The earthquake was there. So people actually then thought, well, that is a proof that it is not really thermal anomaly of the way I described. But then you see here, this box here is enlarged here. This is where the epicenter was. Epicenter is nothing but the vertical projection of the moment of the place where the first rupture occurred, the initiation of the earthquake. It does not reconsider in which direction or over which distance the earthquake would happen. The epicenter is just defined as this particular point, vertically projected on the Earth. If the slope of the fault is dipping at depth, it might well happen actually major displacement over here. But what is more important is this is the area where the maximum infrared emission comes from. This is the area where there's a 25 centimeter uplift, the red color, or a 25 centimeter down subsidence, down movement of the Earth. So this is the area where deep underground, called 10 kilometers, I have to look up the focal depth of this, deep underground, stresses were building up, pushing and moving the Earth overhead in a vertical direction. I'm overrunning. Oh, no, I'm sorry. I'm overrunning already. So we can check this off. And now I quickly go through low-frequency electromagnetic emissions. Oh, I'm sorry. Here you have seen this before. The Alum Rock earthquake, the measuring station was just 2 kilometers from the epicenter. Here is a signal. It's complicated, but these are various stations out of the 70 station network with magnetometers. And this is the station next to these Milpitas, and this may be pre-earthquake pulses. Suddenly, in the middle of the night, between 2:30 and 3 o'clock in the morning, when BART was not operating, though the background is very, very clean and quiet, this is a typical BART noise at this location. There are trains of low-frequency electromagnetic coming out of the ground, indicating there are substantial electric currents flowing, which, in my way of thinking would indicate we are in the final stage of building up stress levels, and you are getting such high battery potential that currents start to flow on a substantial grid. Also, they see these very strange pulses, double pulses of electromagnetic, one polar, sometimes single polar. And when you count these pulses, they're only 10, 20 second long pulses. And you count the pulses per 24 hours intervals, and you plot them as a function of time over, let's say, 3 or 4 months. You see that actually, normally you see these pulses, and they are sometimes related to phenomena that happen in the magnetosphere. Then there's a background of maybe 10 pulses or 5 pulses per 24-hour period. And then suddenly, somewhere 10 days, and this here is 13 days before the earthquake, these pulses come in numbers up to 100 per 24 hours. So there's an increase in pulsation of the Earth in these short pulses, and we have no idea where these pulses are coming from. So the conclusion, and you see I cannot talk about animal behavior and all the other fascinating things, but in conclusion, I think we have a pretty good understanding what are the basic physical processes that can explain ionospheric perturbations, infrared emission, and low-frequency electromagnetic emissions. And now, together with NASA, we are proposing an earthquake early warning system using satellite technology and ground assets, a network of ground stations that would, and with that we can dramatically reduce loss of life and also mitigate loss of property of impending earthquakes. So again, my collaborators that helped me in this work, and thanks for your attention.
Thank you. Is there any questions? You might be able to. Well, it's for the screen.
Okay, well, as long as we have time for questions, how about at least a few words on the strange animal behavior?
It is well known in the medical community, and I may insert that Ipek Gulaci has joined my group because she is a biologist and she had read something that I said to this matter. It is well known in the medical community that positive and negative ions in the air in high concentration have a rather dramatic and opposite effect on human well-being. Positive ions give you a headache. There are actually, in Canada, people have plotted the number of people that, the number of patients coming to emergency rooms with heavy migraines, and suddenly, occasionally they see a bump, and the next day or so there's a local earthquake, magnitude 5 or so in Canada. They don't have big earthquakes, but they have small earthquakes or medium-sized earthquakes. So it is possible that the positive ion emission that we can demonstrate in the laboratory has a rather amazing and strong effect on people and on animals, particularly those that live in the ground, near the ground, because they would be exposed to massive levels of positive ions which affect their behavior. That's our working hypothesis, and we hope that maybe in a year from now we'll be able to report on some laboratory experiment that we are setting up right now at San Jose State University and at NASA Ames to test some of these predictions.
I mean, you've shown that increasing stress in the rock has these effects, but I don't quite understand why the critical stress before an earthquake, why you necessarily are going to be able to predict a time. I mean, you will maybe see rocks stressing, but I don't know, what's the connection between the actual failure in an earthquake and these phenomena?
Yeah, well, this is why I very carefully try to keep away from the word prediction, because prediction is a loaded term that implies that you would be able to really tell exactly time, place, and magnitude.
You'll be looking for increase, places
we
where
are
stresses
looking-
are increasing. Or,
Yeah, we are increasing this, and you must remember that when you take two pieces that are brittle pieces of the Earth's crust, or two rocks, and you push them together at constant velocity. That's what plate tectonics does. When they make contact, imagine that in a Gedanken experiment you can do it, they make contact, then the stress, you continue to push at a constant speed, stress goes through the roof. And the earthquake will happen when the stress becomes essentially exponential. During this accelerated stress per time unit, that's when these processes should occur. But we don't know exactly at which point the failure would occur. This is still, and also the Earth, being so complex, can decide in the last moment not to fracture but to slide. And then you would have a silent earthquake. These things have been described quite extensively in recent literature.
Is there any other questions?
Yeah, I was a little puzzled. Let's see, you had a color graphic of the effects on the ionosphere. There was something up to about, 2.5 hours before the event, or maybe it was 2.5 days. I don't remember now.
No,
But-
it was
okay.
22 hours and so on, right?
Okay, and then you were saying, okay, and here afterwards, you had 2 shots afterwards, and you said that the effect had gone away. But I don't know if you can go back to that slide, but I was not seeing a big difference between the before and after. In fact, 2 of them kind of almost just looked like mirror images of each other. I think you just yeah, okay, so
yes.
that second one down, and then the one in the lower right corner, they're kind of like almost left to right reversals. But to show us a little more in detail what it is that you're seeing there.
Well, you see that little red dot here at the bottom. This is the location of the epicenter in this crosscut. And what the people who are doing this tomography work, and again I should say Regenthaler is doing all this work essentially on a shoestring budget in order to demonstrate that it works before people would be willing to give money to do this in a more systematic way. What he tells me is that we are seeing in this tomography, you're seeing something that can be extrapolated downward, and this is here 200 kilometers, 400, 600. So the Earth's surface would be down here, so the epicenter would be here, and if you take these structures and you would draw a line, it would essentially intersect where this epicenter is, so where the center of this ionization, presumably ionization, occurs. Now, when this earthquake happens, and a few hours later, it takes time for the charge carriers, once they are activated, to go back to sleep. It takes a few hours. They are slowly disappearing, and it looks like after 2.5 hours, as you see here above this area, it becomes normal again, because I remember I mentioned here this is a plot of the perturbation relative to a steady state or long-term average of the behavior of the ionosphere at these different times. So I think these people like Regenthaler and others, also there's a very powerful group in Tiger Liu in Taiwan and in Japan. There are very, very good groups that do this ionospheric work. They are on the right track, and we can provide some understanding why they see these phenomena as they see them.
Is there any other questions? Okay.
So do you know if anyone is working to preserve the energy of earthquakes, to, like you described, the earthquakes could be due to the batteries, right? So could it be used, the energy, not just for generating earthquake, but actually
Right.
to get that energy? Does anyone working on it?
I don't think that there is a prospect of harnessing the energy or the electric current that are produced in these processes, because the current density is still in the order of a fraction of a milliamp flowing through a square meter of cross-section. But if you have a square kilometer of cross-section, you can pump through 1,000 amperes. But then you would have to have a collector area that is also a square kilometer large, and you would get 1,000 amperes out of it, of very low voltage current. Though technically it's not possible to harness this energy as far as I'm concerned. But it's only important from my perspective for understanding these natural phenomena that happen in the Earth.
So I'm wondering, you mentioned, what was it, BART or Caltrain, that could perturb some of the measurements. And can you talk a little bit about phenomena that would cause uncertainty, that it would make more difficult to be able to tell what's going on?
Yes, all these electric measurements or these magnetic field measurements out in the field are heavily perturbed by solar storms. If there is a flare coming and hits, and you get very high activity in the ionosphere, it interferes with whatever you want to measure in the ground. And these are the major natural process. Also, there are the magnetosphere bunches up as the solar wind is passing by the Earth, and the Earth deflects the solar wind, and after it reconnects, and then during this reconnection, the field lines start to bunch up, and they kind of snap together, and these things form these PC1 pulses. That's a term that I heard from the people in the magnetosphere area, and they are also interfering, but that is also effect, of course, most prominent in times of high solar activity. Otherwise, of course, cultural phenomena like BART, like any truck that would move by at half a kilometer or a kilometer distance would interfere with these measurements. But people are pretty good at sorting this out.
I'll have some comments on that. Number one, what you described there on the PC1s and the bunching, you would see in all stations, or many stations, not just one station.
That's right.
The same is true with, they actually went back and looked at all the trucks going by. I mean, they talked to the owner that is living there. They were very, very thorough on this. On the other thing, on the ionosphere, these are really 4 to 5 sigma detection or anomalies. These are huge anomalies that you're seeing there. Normally the ionosphere will not go up to 500, 600 kilometers and extend in such a way. This is really unusual in that extent and in that structure, especially in that tomography there. So.
Yeah, and this is something like Mino said, that anything that comes from the sun hits the whole face, the whole hemisphere, and is detected in all stations. So if there's one station or a group of stations nearby that shows anomalous behavior, you already have an indication that there's something.
Well, and the other thing there is, of course, in these ionospheric perturbations is they are caused by currents in the Earth or by these charge carriers. And these charge carriers have to dissipate, and that takes time. I mean, it's not an instantaneous process. So that's why you have this remnants 30 minutes after, 2.5 hours after.
Right. Yeah.
So
there are wonderful unpublished data from JPL where people were using geostationary satellites. They have a lousy spatial resolution, only 4 kilometer pixels or less, or worse. But they give you an image of the Earth every 30 minutes. And there was this earthquake in Turkey, the Izmit earthquake in August 1999. And it was one of these large disastrous earthquakes that cost 25,000 lives. And using Nevin Bryant at JPL was looking at geostationary METEOSAT, the European weather satellite data, and he saw that along the North Anatolian Fault there were areas of increased infrared emissivity building up before the earthquake, And then when this powerful earthquake hit magnitude 7.4 or 7.6, the seismic wave coming from that earthquake was powerful enough over an area of at least 100 kilometers to either side of the fault to activate these electronic charge carriers. And suddenly, in the infrared image from the geostationary satellite showed that the whole northwestern part of Turkey was lighting up in the infrared, stayed there for about 2 hours, 1.5 to 2 hours, and then died back. And that is, now we understand that once we squeeze the rock is angry at us. We have to wait for several hours for the rock to quiet down, for the charge carriers to find time to recombine, and this takes a few hours. So therefore, I think that during this event of the seismic waves that are generated by the Izmit earthquake, the whole region became a source of these charge carriers. For a very short period of time, these charge carriers came to the surface and stayed there and caused this infrared emission for about an hour and a half before they went back to bed and fell asleep again.
Well, I'd like to thank you all for joining us for the talk today. Please help yourself to some refreshments out in the courtyard. Okay, thank you.
Thanks, Tammy. Thank you so much.